In this video, we're going to take a look at double angle identities. And we're going to start by deriving these double angle identities. It turns out that these are pretty easy to derive if you're using the sum and difference formulas that we've looked at in a previous video for sine and cosine. So for the sine, the double angle identity for sine, the sine of double some angle, in this case theta, so the sine of 2 theta, we could rewrite as the sine of theta plus theta. That's what 2 times theta means. It means just adding theta to itself. So that puts this in the form of the sine of some angle plus some other angle. It just, in this situation, the angles happen to be the same, but I can still use it. So I'm going to say that this is equal to the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. I'm just following this sum identity for sine to come up with those. So what is the sine of theta times the cosine of theta? They're not like terms, so they just have to stay that way. What is the cosine of theta times the sine of theta? Not like terms, they have to stay that way. However, the commutative property of multiplication tells us that the order does not matter in terms of how we write multiplication. So the cosine of theta times the sine of theta can be reversed into the sine of theta times the cosine of theta. Now, why is that important? Well, because now we have like terms, don't we? So now we have 2 sine of thetas and cosine of thetas. And it turns out that that is the double angle identity. Let's go ahead and look at the cosine of 2 times theta. Again, we're going to rewrite this as the cosine of theta plus theta, and then we're going to use our sum identity for cosine down here on the bottom that says that this is going to equal the cosine of the first angle times the cosine of the second angle, which just happens to be the same, minus the sine of the first angle times the sine of the second angle. Now, cosine of theta times cosine of theta is simply cosine squared theta. There it is. Minus sine of theta times sine of theta is sine squared theta. So that is a double angle identity for cosine. But it turns out that there are some variations of the double angle identity for cosine. And those come from the Pythagorean identity that says cosine squared theta plus sine squared theta is equal to 1. One of those variations would come from rewriting the sine function, the sine squared, rewriting this sine squared, solving it for sine squared. So subtracting cosine squared theta from each side. Here's what that allows me to do. That allows me to rewrite cosine squared theta minus sine squared theta as cosine squared theta minus, now I'm going to substitute in what sine squared equals, and sine squared theta equals 1 minus cosine squared theta. Again, this is just a variation. It's coming from a variation of the Pythagorean identity. Now, if I distribute that negative, right, I have to distribute that negative, I get cosine squared theta minus 1 plus cosine squared theta. And that's going to give me, looks like I've got 2 cosine squared thetas, so I'm going to call this 2 times cosine squared theta minus 1. And that's another double angle identity for cosine. One more, let's do, instead of solving for sine squared like we just did, let's solve for cosine squared. And so we're going to say cosine squared theta is equal to 1 minus sine squared theta. So now I'm going to rewrite the cosine. So this whole piece gets rewritten, and I'm going to call that 1 minus sine squared theta. and then I'll just tack on that minus sine squared theta that was already on the end. And now I've got 2 of those sine squared thetas, so I'm going to call this 1 minus 2 times sine squared theta. And that is another variation of the double angle identity for cosine. Now you might be thinking to yourself, why do I need 3 of those double angle identities for cosine? You don't necessarily, because with this first one that we listed, the cosine squared theta minus sine squared theta, with that first one, you can always derive the other 2. But there are times when you're being asked to find the cosine of a double angle, and maybe you're only given cosine. So in that case, maybe you want to use the identity that only involves cosine, or maybe you're only given something about sine, so you want to use the identity for double angle that only involves sine. So it just gives you more options, and we'll look at some examples of this in just a minute. So as a summary, the double angle identities for sine and cosine are listed here. Double angle identity for sine, there's only one, so that's sort of nice. You don't have options. Sometimes it's nice not to have options. You just know what you're going to use. The sine of 2 theta is always equal to 2 times the sine of theta times the cosine of theta. Always going to equal that. For cosine, we have 3 options for double angle identity. The cosine of a double angle can equal cosine squared theta minus sine squared theta. We saw that we could also manipulate that a little bit using the Pythagorean identity to say that it also equals 1 minus 2 times sine squared theta, or 2 times cosine squared theta minus 1. So let's try an example and see what we need to do in order to find these double angles. So this first example says, given that the cosine of some angle theta is equal to negative 2/5, with theta being between pi and 3 pi over 2, find the exact value of, in part A, the sine of 2 theta, and part B, the cosine of 2 theta. All right, so part A, I'm going to say that the sine of 2 theta, we know that that's equal to 2 times the sine of theta times the cosine of theta, right? That's just using the identity. And it looks like the cosine of theta has been given to us, hasn't it? So the 2 is set, and the cosine of theta is also set, right? What does the cosine of theta equal? The cosine of theta equals negative 2/5. So I'm just going to put a negative 2/5 in that position. That's what the cosine of theta is equal to. Now, the piece that I'm missing is what the sine of theta is equal to. That has not been given to me, so I need to calculate that, and I'll do that off to the side. I can either use the Pythagorean identity, or I can use the idea that cosine is equal to the ratio of x over r. I'll go ahead and use the Pythagorean identity because we just talked about that, so it feels like that's in our head, right? So sine squared theta plus cosine squared theta is equal to 1. And so sine squared theta plus negative 2/5 squared is equal to 1. Sine squared theta is going to equal 1 minus negative 2/5 times negative 2/5 is what, 4 over 25. So I'm going to say 4 over 25. Notice I'm not using the calculator here. 1 can be rewritten as 25 over 25. So 25 minus 4 is 21, isn't it? So sine squared theta can equal 21 over 25. Okay, challenge yourself to see if you can do some of these things without a calculator. And now I'm going to square root each side, and so I'm going to get that the sine of theta is equal to plus or minus, right? We got to do plus or minus the square root of 21, which doesn't reduce, over the square root of 25, which is 5. Now notice I said plus or minus, but I didn't write it down because I'm going to decide right now whether it's a plus or a minus. And how do I decide that? Well, that comes from the fact that theta was given to me in the third quadrant, right? Theta is between pi and 3 pi over 2. Now, in the third quadrant, right, not only is my cosine negative, but my sine is also negative. So this square root of 21 over 5 needs to be negative, okay? So in the place of the sine of theta, I'm going to put in negative square root of 21 over 5. Okay, and so my final answer here is just going to be multiplying all that out. Up in my numerator, so this 2 is 2 over 1, isn't it? Up in my numerator, I've got 2, I'll just write this out for you, 2 times negative square root of 21 times negative 2. In the denominator, I've got 1 times 5 times 5. So that gives me, let's see, 2 times 2 is 4, and then I've got a negative times a negative, so it looks like I'm going to have 4 times the square root of 21 on the numerator, and 1 times 5 is 25. So that is my double angle for sine. All right, let's do part B. Now, for part B, the cosine of 2 theta, I have choices. I can either use the identity that involves both sine and cosine. I can use the identity that only involves sine. I can use the identity that only involves cosine. Now, in this situation, I really could use any of these three, because not only do I know what the cosine of theta is equal, that was given to me, but I also calculated what the sine of theta is equal to. So you can use any of these. What I usually do is play it safe, and I will use the identity that involves the thing that was given to me. In this case, the cosine was given to me. So I'm going to use the identity that only has cosine in it. And the reason I do that, you've seen me with this sort of technique before, is because if I've made some mistake in my calculation for sine, I don't want to compound that error in my cosine for the double angle. So I'm going to use the thing that was given to me. Okay, so I'm going to write 2 times cosine of theta is equal to negative 2/5, and I'm going to square that. That's what cosine squared theta is equal to, minus 1. What is that equal to? Well, that's equal to 2 times, let's see, negative 2 times negative 2 is 4, and 5 times 5 is 25. And then I'm subtracting 1 from that. So it looks like, remember this 2 is over 1, it looks like I'm going to get 2 times 4, which is 8, over 25 minus 1. And 1 we could call 25 over 25, couldn't we? And so 8 over 25 minus 25 over 25, I believe, I'll let you calculate this on your own, is negative 17 over 25. Now, one thing that you may be wondering about is when you're in a situation where you have like the negative 2/5, right? We have this negative 2/5, and I think you heard me verbally say it's negative 2 times negative 2 over 5 times 5. How do you determine where that negative goes? I want you to remember that a negative number, so when we have something like negative 2/5, that is equal to either negative 2 over positive 5, or that's equal to 2 over negative 5. I just chose to write it with the negative in the numerator, simply because I'm thinking in terms of, x's over r's or y's over r's, where typically our r is not going to be negative. But it doesn't actually matter. Either way, this would have worked out the same. What negative 2/5 does not equal is a negative over a negative, because a negative over a negative would give us a positive, so that would not be true. So that's just a refresher of some basic arithmetic that I've seen students make mistakes with. Now let's derive the double angle identity for tangent. And like we did with sine and cosine, we're going to make use of the sum or difference identities for tangent that we've derived in previous videos. The tangent of 2 theta we can rewrite as the tangent of what 2 theta represents, which is just theta plus theta. So now I can use the sum identity for tangent to say that that is equal to, up in the numerator, I'm going to have the tangent of the first angle plus the tangent of the second angle, both thetas in this situation. So I'm using this identity right here. Down in my denominator, I'm going to have 1 minus the tangent of theta times the tangent of theta. And there's not a whole lot of simplification I can do, but what I can do up in the numerator is rewrite the tangent of theta plus the tangent of theta as 2 times the tangent of theta over, in the denominator, 1 minus tangent of theta times tangent of theta is tangent squared theta. And that's about as far as we can go. So if we're being asked to find the tangent of a double angle, which we'll see here in just a minute, we will need to know something about the tangent of theta. So we'll see that in just a bit. Now let's look at an example, or continue our example that we looked at before, but do it now for tangent of the double angle. So we know that the double angle identity for tangent is that the tangent of 2 theta, is equal to, in the numerator, 2 times the tangent of theta, all over, in the denominator, 1 minus tangent squared theta. All right, now this is the same example that we saw previously, and we already calculated, this is just what we already did. So the sine of 2 theta is equal to 4 times the square root of 21 over 25. If you go back and look at your notes, I think you'll agree that that's what we came up with. And then we also came up with the idea that cosine of 2 theta is equal to negative 17 over 25. So we're just going to continue this now and say, okay, well, if that's true, what is the tangent of 2 theta? So the tangent of 2 theta is going to equal 2 times the tangent of theta. Now, do we know the tangent of theta? I better stop here for a second. What is the tangent of theta? So off to the side, let's figure that out. Well, the tangent of theta is equal to whatever the sine of theta is over the cosine of theta, right? Do we know what the sine of theta is? Go back and look at that example, and I think that we did calculate it, didn't we? The sine of theta is equal to negative root 21 over 5. And of course, the cosine of theta, that was given to us as negative 2/5. So I can simplify this. Negative square root of 21 over 5 times the reciprocal is negative 5 over 2. 5's cancel out. It looks like, let's see, a negative times a negative, that the tangent is going to be the square root of 21 all over 2. All right, make sure you agree with that. So I'm going to take that square root of 21 over 2, and I'm going to substitute it in the formula, or the identity, where it belongs, right in this position. Now I can already see that, this 2 that was in the front, that's 2 over 1, right? So the 2's, that's going to be nice, right? Those 2's are going to cancel out, but we're getting ahead of ourselves. Let's go down into the denominator. That's going to be 1 minus the tangent of theta, which we said was square root of 21 over 2. We're going to now square that, okay? So let's see here. Now what do we have? We have, up in the numerator, we're going to have just the square root of 21. Down in the denominator, we're going to have 1 minus square root of 21 times the square root of 21 is 21, and 2 times 2 is 4. All right, so what is 1 minus 21 over 4. Well, you know, you've seen me do this before. I'm going to rewrite. I'm going to think of 1 as really just 4 over 4. How about that? And now I can do that subtraction. So I'm going to get square root of 21 over 4 minus 21. What is 4 minus 21? I think that's negative 17. Negative 17 fourths. And if I take that negative 17 fourths and I multiply by the reciprocal, I'm going to get negative 4 times the square root of 21 all over 17. That's what my tangent is equal to. Now, while I was doing this, I was thinking to myself, I wonder, and I'm going to see if I can squeeze this in, I wonder if the tangent of 2 theta, could that equal the sine of 2 theta over the cosine of 2 theta? Maybe you were thinking that as well, especially when you saw me do it here. Is that true? Well, let's try it. We know what the sine of 2 theta is. The sine of 2 theta is 4 times the square root of 21 over 25. And right, that just came from what we figured out in part A. And the cosine of 2 theta is negative 17 over 25. Instead of dividing by that, I'm going to multiply by the reciprocal. So that's going to be negative 25 over 17. All right, 25s are going to cancel, and it looks like I'm going to end up with, up in the numerator, I'm going to have negative 4 times the square root of 21 all over 17. And sure enough, they are the same, aren't they? So if you already know the sine of 2 theta, and you already know the cosine of 2 theta, you can just directly use that to come up with the tangent of 2 theta. Now, if you don't know sine of 2 theta, and you don't know cosine of 2 theta, then what you want to do is make use of the double angle identity that only involves the tangent. So you get to choose. In earlier sections, we've learned how to verify identities. So let's try doing that here to verify another form of the cosine of 2 theta. And to do that, we're going to use the double angle identities that we already know for cosine. That'll help us sort of know what we're headed toward or what we're trying to achieve. When you verify an identity, you always want to start, at least I like to start, with the more complicated looking side. So that, in my opinion, is definitely the left-hand side. So up in the numerator, and let me just read this out for you. Verify the identity in the numerator, cotangent of theta minus tangent of theta, all over, in the denominator, cotangent of theta plus tangent of theta. So exactly the same, but one's a plus and one's a minus. Does that equal the cosine of 2 theta? All right, so here's what I'm going to do. I'm going to look at that numerator. I'm going to rewrite the cotangent of theta. I'm going to rewrite that as, and I'm going to need a lot of space here, so I hope I've got it. That's going to be the cosine of theta over the sine of theta. And the tangent is sine of theta over cosine of theta. All right, same thing down in the denominator, but now we have a plus sign in the middle. All right, so now what? How do I make that look better? It looks horrible. Well, I think I'll actually do that subtraction. And I can do that subtraction or that addition if I have a common denominator. And I can get a common denominator. Up in the numerator, I'm going to multiply, right? The common denominator is going to be sine of theta, cosine theta, and same thing down here in the denominator, right? So I'm going to multiply this first term by cosine of theta over cosine of theta, and I'm going to multiply the second term by sine of theta over sine of theta, right? I'm going to do that also down in the denominator, so I'm just going to go ahead and write it here. Exactly the same thing. Remember, these are exactly the same except for one's a minus and one's a plus, right? Okay, so now let's simplify this. In the numerator, this big ugly numerator, I'm going to have cosine of theta times cosine of theta minus sine of theta times sine of theta. So that's going to be cosine squared theta minus sine squared theta. I always like it when I have cosine squares and sine squares because I'm already thinking Pythagorean identity, but we'll see what happens. And we're going to have down in the denominator of the numerator, right, you're going to have cosine, let's see here, I'm going to have cosine of theta times the sine of theta. Okay, now in my denominator, I'm going to have cosine times cosine plus, sine times sine. So that's going to be cosine squared theta plus sine squared theta. And that's going to be over that common denominator again. So those common denominators, because they're the same, right, those guys are going to cancel out. And so I'm going to be left with, let's just take a look here. And I don't usually like to write this. I wish I had more vertical space, but I don't, so bear with me here. I'm going to have, let's see, cosine squared theta minus sine squared theta, up in the numerator. And down in the denominator, what is cosine squared theta plus sine squared theta? That's really nice, isn't it? That's equal to 1. And it's equal to 1 because of the Pythagorean identity, isn't it? So cosine squared theta minus sine squared theta, that is one of our identities for the double angle for cosine. So that's going to equal cosine of 2 theta, which is exactly, right, that's exactly what I wanted it to be. So we have now verified this identity. It's a little ugly, but we have verified the identity, haven't we?